All right. Well, hi everybody. It's great to be here. I haven't been on a Zoom call in a while, so I'll just, I guess I'm talking to my computer. But I see there's a lot of people here, and I even recognize some names. So this is pretty exciting for me to be able to present to Oregon Wild. And well, let me get on. Let me just share my screen and. Let's see. Um, and okay. So this talk basically comes out of writing these roadside geology books of Oregon and Washington, and then to some extent the Oregon Rocks book. And I think one of my greatest joys in visiting these places is not just learning about them, but also photographing them, because I've been into photography for a long time. And I guess that's one of the things, is there's so many amazing landscapes in Oregon and Washington that it was always really exciting to travel around and feel like I had some legitimate reason to be there because I was working on this book. But in many ways, I was just kind of geo-touring around. So we can start with the slides. I'm sure everybody here realizes just what amazing landscapes we have. This is a view of Bandon Beach, where you can go visit the sea stacks at low tide. If you go to the east, you get up into the Cascades. Those are the Three Sisters on the right, and Mount Bachelor in the background here, and Broken Top on the left. If you go up to Washington State, you can see more of the Cascades. They go actually from Northern California all the way to just north of Vancouver, British Columbia. And so here's a view of Mount St. Helens looking north towards Mount Rainier. And if you go to the northern part of Washington State, you get into the North Cascades Range, which they're not active volcanoes. They originated as metamorphic and igneous rock. Excuse me. I've been talking a lot today, so I'm a little bit hoarse, but they originate as igneous and metamorphic rock deep in the crust, and they have since been uplifted, and you can see they're being deeply eroded by glaciers. If you go east of the Cascades axis, you get into much drier climates. This is looking into Yakima Valley from in northern Washington State. And if you go down to southern Oregon, you can get into the Great Basin and the Basin and Range Province proper. There are a lot of amazing playa lakes down there. This is the Alvar Desert, which you can see is flooded in this photo. And then later on, it dries up and leaves this beautiful playa with mud cracks and just amazing views. So just looking at a physiographic map of Oregon and Washington, you can see that there's just a lot of variability, and they break into these different physiographic provinces, which was really very convenient for writing these books, because each province could act as a separate chapter in the book. And so each chapter would have an introduction to the province, and then followed by road guides for the main roads in each of those areas. And that's the physiography, though, but that's really reliant on the geology. And so here's a schematic cross-section across Oregon. And it's pretty complicated, but what I really want you to see is this heavy red dashed line right along here. And that separates the so-called basement rock from the cover sequence. And so what I'll be doing in this talk is I'll be talking about the basement first. And to talk about that, I'll be talking about the area called Siletzia here in purple. And then after that, I'll talk a little bit about the boundary here with ancient North America in northeastern Washington. And then I'll talk about the cover sequence. And to do that, we'll look at some features in the Columbia River Gorge. But before going on, I want to make sure everybody's kind of up to date on plate tectonics, because plate tectonics is what's really controls so much of the geology in the Pacific Northwest. I want everybody to be on the same page. So what we see in plate tectonics is that the Earth's outer shell, called the lithosphere, is broken into these large fragments called plates. And as the plates move around, they cause volcanic eruptions, they cause mountain building, and they cause earthquakes. And here in the Pacific Northwest, you can see there's 3 plates. There's the Pacific plate in yellow, the Juan de Fuca plate in blue, and the North American plate. So the next slide will be a close-up of that area. And here's the Pacific plate. It's turned gray, and the Juan de Fuca plate in blue. And then beginning here at the Cascadia subduction zone, you've got the North American plate. And you'll notice the Cascade volcanoes here, they trend parallel to the Cascadia subduction zone. And so what's happening here, and these are some of the Cascade volcanoes, the photograph on the right, which I shot out of a commercial jet flying probably to Denver or something like that. And anyway, so the Juan de Fuca plate is pulling away from the Pacific plate, and it's sinking underneath North America at the subduction zone. So in sort of 3 dimensions, it looks something like this, where the Juan de Fuca plate, it sinks underneath North America. And what happens as it's sinking is it heats up, and as it heats up, it causes it to dehydrate, which drives a lot of water off of the plate, and it rises up into the overlying North American plate, which is really hot, but not melted. But the presence of that additional water causes melting in the North American plate, which makes magma, which fuels the volcanoes. So that's why the volcanoes form this line parallel to the subduction zone. Well, this plate tectonic activity has been going on for a long time in the Pacific Northwest. And we can see that from looking at the rocks. Here are some of the active volcanoes. These are the 3 sisters, and you can see they're making their line. But if you think about these volcanoes, they're being fed by magma from below. But not all that magma makes it up to the surface. A lot of it cools and crystallizes beneath the surface as an intrusive igneous rock. And probably the best known of those is granite, which we can see in a lot of places. This granite down here is in Mount Rainier National Park. We've got granites in the Western Cascades here in Oregon. There's a lot of granites up in the Okanagan and the North Cascades of Washington, and there's granites in the Blue Mountains and the Klamath Mountains of Oregon, and they get back older than 140 million years, some of them. And so this process has been going on for a long time. But it's also really important as far as how the continent grows, and that's this diagram down here on the right, continental accretion. And you can imagine a topographically high area, say an oceanic plateau or something, coming into the subduction zone, and as it comes into the subduction zone, it's going to jam it up, and by jamming it up, it's basically stops the subduction, but the 2 plates are still converging with each other, and so eventually it's going to break farther offshore into a new subduction zone, and in so doing is going to add or accrete this topographically high area to the continent. And you can imagine then another, maybe an island arc or something coming along later on, and it'll do the same thing, and it'll get added. So you'll have one added body, one accreted terrain after another being added to North America. And so if you look back at that cross section, that's basically what you see. Here's the edge of the North America at the end of the Paleozoic era, even a little younger than that. And these are all successive terrains, and that is the correct spelling, by the way, of terrains, added one after the other to the edge of North America. And finally, the last one that was accreted was Siletzia. That's the basement. And if you look up at Washington State, it's pretty much the same thing. You've got one terrain after another. This NC stands for North Cascades, Q stands for Cornelia, and they're actually whole collections of terrains. And then overlain by that, of those terrains, is the cover sequence. So with Siletzia, we can see that in a lot of places in Oregon and Washington, and one of its hallmarks are these shapes in the rock. This is basaltic lava, but it's got these rounded shapes, which we call pillows. And these form in undersea eruptions. And you can imagine a volcanic vent expelling bits of lava, which then will cool very quickly, pretty much instantaneously on contact with the cold seawater. But the inside of it will stay malleable, so it kind of settles down and will conform to the seabed. And then more lava will erupt over the top of it. And so they're all kind of conforming, their shapes all kind of conform with each other, and they make these blobs we call pillows. And we see this, it's one of the characteristics of Siletzia. It's not all pillow basalt, but a lot of it is. And so here's some more pillow basalt. In cross-sectional view, you often see these sort of radial fractures, which are cooling fractures. And on the geologic map, you can see Siletzia in purple. It starts down here near Roseburg. And you can see wherever there's purple, you can see Siletzia. Those are all exposures of Siletzia. It goes all the way up actually to southern Vancouver Island. It's just, this is an American map, so it doesn't include Canada. So Siletzia formed between about 50 and 56, 57 million years ago. And then it was accreted between 51 and 49 million years ago. And then after it was accreted, more sediment and some volcanic material was deposited over the top, something akin to this. And that's what all these other colors are. So if I were to say drill a well right here in what's called the Tyee Formation, I would go down through the Tyee Formation and eventually into the basement, which is Siletzia. And if we were to go up here to northern Washington, we can, here's Siletzia again, makes this big horseshoe. You can drive right through the exposures of Siletzia on the Hurricane Ridge Road, and you can see these amazing exposures of it, these pillows. I mean, there's lots of pullouts. You can go out, you can pet the pillows, get a good look at them, and then continue driving through the basalt and then into the core of the Olympics, which is shown in green, and then these lighter kind of yellow, sort of light green colors. And this is the view that you get up at the top of the Hurricane Ridge Road. Mount Olympus is back there, but you're now in what's called the Olympic Subduction Complex. So all this is that Olympic Subduction Complex, and this is material that's been scraped off the subducting plate and added onto the edge of North America. And you can see here, Siletzia is actually faulted up and over the top of the Olympic Subduction Complex along what's called the Hurricane Ridge Fault. But because it's a subduction complex, it's really highly deformed. So it's internally faulted and folded, and it's really, really variable. So if you were to look at it up there at the Hurricane Ridge Road, you'd see that you had some metamorphic rocks. And then if you go down here to the coast, you can see exposures of it where there's different kinds of non-metamorphic rocks. There's sedimentary rocks that haven't been metamorphosed. So if you go down to the coast, you can see these beautiful landscape features. There's an arch here at Second Beach. But if you look at the rock closely, you can see that it's sandstone, and it's all broken up. And then here's a piece of limestone stuck in the middle. So these are submarine debris flow deposits. And there's more of them. If you go, say, to Ruby Beach, you can see more debris flow deposits here. And then if you go, say, to Beach 4, which is right along the coast, right along the highway, you can see you've got more, nicely stratified sedimentary rocks. And you can see they're tilted, so it kind of makes more sense. But then if you take a look at these rocks closely, you can see that actually they're overturned because they exhibit these features called graded beds. So if you imagine sediment settling out of suspension, the coarsest grained sediment will settle to the ground first, and then it'll get finer and finer upwards. Well, here, if you look at it, it's coarser grained here, and it gets finer and finer in this direction. Another coarse bed, and it gets finer and finer in this direction. And then another coarse bed, finer and finer in this direction. So it's getting younger as you go downwards, which means these rocks were deposited horizontally, tilted past vertical until they are completely overturned. And if you go around the corner, you can see that they're all, in some places, they're really tightly folded, and there's even a fault right here in between these upper rocks and the lower rocks. So there's a lot of deformation there, and the rocks are really quite variable, which is what you might expect for stuff that gets scraped off at a subduction zone. And now here's a map showing all the accreted terrains on the west coast of North America, shown by the different colors. And in gray, you can see the edge of Paleozoic North America, onto which all these accreted terrains were added. And you can see Oregon and Washington. You'll notice that Oregon doesn't have any of the old continental margin on it. And because of that, here's a fun fact. Oregon has the shortest geologic history of any state in the conterminous U.S. And that's because the margin of or the old continent has rocks as old as they're Precambrian in age. So they get, the youngest of those Precambrian, well, the basement rocks get as old as over 2.5 billion years old in some places, but a lot of places younger than that. But still, Oregon doesn't have any Precambrian rocks in it. The oldest rock Oregon has is Devonian in age, which is somewhere around 350 million years old. You can see there's a little bit of the Precambrian margin in northeastern Washington. And you can also see here's the Olympic subduction complex and Siletzia in purple. But this raises a question as to how do you know if you are on accreted basement rock or the ancient North America? And it's often very difficult to tell because you might be up in the cover. But there are some things that can clue you in, at least as far as if you're on ancient North America. And to illustrate that, we can take a quick look at the Grand Canyon, which is about where this red star is. And the Grand Canyon, besides its basement rock down here, which is 1.7 billion years old, has a sequence of sandstone, shale, and limestone, which was deposited during the Cambrian period when the ocean moved up onto the continent. And we see that same sequence of rock of that age throughout much of Western North America. We can see it here in the Grand Canyon. You can see it up in Utah. You can see it in Montana, see it in Colorado. I taught for a few years in Eau Claire, Wisconsin. We had that sequence in Wisconsin. So it's a very common feature throughout much of the old continent, but it's not on the accreted terrains because they weren't part of North America then. Now, if you were to go up here to northeastern Washington, you can get to this place, which is one of my favorite spots. It's called Sweet Creek Falls, quite different from the one here near Mapleton. But what you can see in this photo are these cobbles. These are quartzite cobbles, and quartzite is a metamorphosed sandstone. And these are part of the Addy quartzite, which is a Cambrian sandstone. And if they came from upstream, and if you were to go upstream, you could find outcrops of this Addy quartzite overlain by shale, overlain by limestone. And then that in turn is overlain by this material, which started off as a shale, and it's a little bit younger, it's Ordovician in age. So these rocks were deposited on the old continent up in northeastern Washington. So that was right about here near Medellin Falls. And you can get on Washington State 20 and you can drive west and you can leave North America behind and drive across the Okanagan, which there's a whole series of terrains there, part of the much larger terrain called Quinella. And then you can keep driving and drive across all the accreted terrains of the North Cascades, and eventually take a ferry across to the Olympic Peninsula, and you're back on Siletzia. So by driving Washington State 20, you can pretty much just check out all the accreted terrains of Washington State, and the road will take you up into the cover in various places, and you can see those rocks as well. Now, the accreted terrains, or the basement rock of Oregon and Washington, is exposed wherever on this map, wherever it says exposed accreted terrains. Now, there's a lot of cover there as well, but this is where you can actually see it. In these other areas, it's all cover. You don't see any exposures of the accreted terrains. And that's what I want to talk about now, because we can look at features in the Columbia River Gorge, which pretty much goes from Portland to the Dalles, and look at features in the cover in the Columbia River Gorge, just to get kind of a sense of, well, the complexity and some of the amazing things in the cover. So here's two geologic maps, one from the roadside book of Oregon down here, and the other from Washington, and they're just stuck side by side. So the river's not this wide. You can see there's actually two Columbia rivers in this slide. So there's only one, but you can see a lot of the cool features you can see along the highways, and there's a lot of different rock types shown by the different colors. And I tried to simplify that here a little bit, but you can see there's still an awful lot of them. But the main things I'm going to want to talk about are the Columbia River basalt, which are shown here in these various brown colors. You can see there's three parts of it. And also a little bit of mention goes towards the early Cascade volcanic and sedimentary rocks in these more bright colors. And those are important because they speak to the age of the whole Cascades volcanic system. And then there are these other rock units over here, which we don't have time to talk about really, but I will talk about landsliding and some of the river and flood sediments towards the end of the talk. So the main things I want to point out is that we've got volcanic activity. It dates back to the early Cascades, and I'll focus really on the Columbia River basalt group. There's some explicit evidence in the Columbia River Gorge that the age of the river itself that dates back more than 12 million years, which I think we know from other reasons too, but it's kind of nice to see some real clear evidence for that. We'll see that the bedrock structure, which is the overall inclination of the rocks, that really controls the shape of the gorge. And then talk briefly about the Ice Age floods, which roared down the gorge between about 18 and 15,000 years ago. Okay, so the Columbia River basalt, it really gets its start here in eastern Oregon. These are the Wallowa Mountains back here, and all of these rocks, these are all lava flows of the Columbia River basalt group, and they started basically as these feeder dikes, which were fissures in the ground, and they flooded the landscape. And you can see what a huge area they covered, and they flowed all the way down the gorge and out to the ocean. And so when we go into the gorge, this is near the Dalles, well, sort of between the Dalles and Hood River. Everything in this photograph consists of Columbia River basalt group. So we're all the way down here, and it's all Columbia River basalt group. And this area in the map here covers 81,000 square miles. And the lava was erupted between 17.2 and 6 million years ago, and it created a volume of 52,000 cubic miles, 94% of which was erupted by 15.6 million years ago. So much of that, about 40, if you do the calculations, like 49,000 cubic miles were erupted in a period of just 1.5 million years. Now it's like impossible to get your mind around how much this is, but you can work it out. This would cover the conterminous United States to a depth of 80 feet. There's so much lava. And it followed the path of the ancestral Columbia River all the way out to the coast. It also consists of a number of different units. You can see here the picture gorge basalt was actually the first one. That's what you can see near John Day. But all of these were erupted till about 14.5 million years ago. And then the Saddle Mountains basalt was the last one. And you can see its relative volume is really insignificant. But it's these three, the Grand Ronde basalt, which was the most voluminous, and the Wanapum basalt, and then Saddle Mountain, the older part of the Saddle Mountains basalt. That's what we'll see in the Columbia Gorge. So starting with the Grand Ronde basalt, you can see it at Multnomah Falls. There's over 600 feet of it. That's the height of the waterfall. You can see also there's a number of different lava, different flows. Like here's the base of one. Up here you can see this is the base of another. And if you look at this upper flow, it's really got a lot of texture to it. And if you zoom in on that, you can see that that texture is because it's made out of pillows. So this is a pillowed lava flow, and it didn't come because it erupted under the sea. It got the pillows because it flowed into a lake. And so from this, we can infer that there were lakes along the Columbia Valley along which the river was flowing. And then if we go up to the Dalles, this is Wanapum basalt right at the intersection of US 197 and US 30. So this is literally 3 minutes off the interstate, and there's a big pullout. You have no excuse not to stop at this great road cut. And so here we're looking at the Wanapum basalt, which now is the second youngest in that group in the gorge. And you can see it's full of pillows here, but it's all one flow. It grades up into these columns, and you can see that it's a gradational contact because the pillows just kind of fizzle out and you start getting more solid pieces of the flow above it. So the interpretation here would be that the lava flowed into a lake, started making all these pillows, but then it filled up the lake and it kept flowing over the now filled up lake. And then when it cooled, it made the columns, it was on land. So one lava flow showing the whole evolution and the filling of a lake here. And then we can see the youngest basalt, the Saddle Mountains, up at the top at Mitchell Point. Down here, you can see the Grand Ronde basalt, and you can see they're tilted. And you can, if you zoom in here, you can see these rocks, they look a little different than the basalt up at the top. And that's because these are river gravels. These are river gravels of the Columbia River. And they have to be older than the Pomona member here of the Saddle Mountains basalt, because they're underneath it. So we've got right here, this is clear evidence that the Columbia River was around prior to 12 million years here. But then where's the Wanapum basalt? Because the Grand Ronde basalt is the oldest one in the gorge. Saddle Mountains basalt is the one on top, the Wanapum. And you can see the Wanapum from another view. which is right here. So here are those river gravels. Here's the Saddle Mountains, and here's the Wanapum basalt. And you can see that the river gravels are basically running into the Wanapum. So this was an old river channel that the river gravels cut into, basically an old canyon that the river gravels filled up. So at Mitchell Point, just to kind of summarize all that, we've got the gravels. They demonstrate the antiquity of the Columbia River, at least older than the 12 million year Pomona flow of the Saddle Mountains basalt. And they were deposited in a canyon, which suggests uplift prior to 12 million years ago to create that topography so it could erode into a canyon. And you'll also notice these rocks are tilted to the south. And that's really important coming up right now, because that southward tilt really affects the overall shape of the Columbia Gorge. Here's a view looking up from Cape Horn, and you can see that the south side of the gorge, north side of Oregon, is really steep, whereas the south side of Washington is really quite gentle. And that's because there are all these big landslides on the Washington side. This is the Skamania landslide. And I mean, it goes all the way, here's the head wall. It goes all the way from here, almost up to Beacon Rock, right up there, not quite all the way. But also this rock in the middle of the river is part of that landslide complex. And so you can see, because of the landslide, it just makes for a gentler topography. And the reason you get these big landslides on the north side is because the rock is tilted to the south, just like it is at Mitchell Point. And that south-directed tilt means that things can slide down towards the river. On the south side of the river, though, there's nowhere for them to slide. So you can get some landslides, some smaller ones, but you just don't get anything the same size that you do on the north side of the river. That effect is further enhanced because the lava flows are typically fractured, and so they're quite permeable to water soaking through them. And they get down into this Eagle Creek Formation, which is also very permeable, and the water keeps sinking down until it hits the top of this rock unit called the Ohanapikosh Formation. And there's an old ancient soil there that's very impermeable. And so the water tends to pool right along here, and that tends to buoy everything up and can facilitate the sliding. And these two are the two older Cascade rock units. The Ohanapikosh gets back as old as about 40 million years. So its presence indicates activity in the Cascades volcanic chain dating back that far. But anyway, you've got these landslides because of that, that geometry of the rocks, and because they can allow water to soak through and pool at the top of the Ohanapikosh. Here's a view of another one of the landslides. This is the Bonneville slide. Here's Bonneville Dam right here. And oh gosh, here's the Bridge of the Gods. And I'm suddenly drawing Cascade Locks. Here's Cascade Locks looking down on it. And you can see the landslide here. It slid about 600 years ago. And you can see it pushed the channel of the river to the south. It actually dammed the river, gave rise to the Bridge of the Gods legend, where you could actually apparently walk across the river without getting your feet wet. And in damming the river, it backed it up to make a really big lake that went as far as the Tri-Cities area, which then eventually broke through the dam and flooded downstream, and it would have flooded downtown Portland to a depth of about 20 feet, which is nothing compared to the Missoula floods, which came down the canyon between about 18 and 15,000 years ago. Here's Vista House at Crown Point, and the largest floods would have crested here. They crested about 100 feet above Vista House. So you can imagine just how big these floods were, positively immense. And for those of you who don't know the story of the Missoula floods, they originated here in Glacial Lake, Missoula. And Glacial Lake, Missoula formed because the Cordilleran ice sheet was flowing down into what's now the northern part of the US. And there's a series of lobes. Here's the Puget Lobe. And this lobe over here blocked the Clark Fork, which is a river that drains northwestern Montana. And much the way that that landslide dam blocked the river 600 years ago, this ice tongue dammed the river and caused a big lake to fill up behind it. But look at the scale of the lake. It's 100 miles to Missoula, if you see the scale down in the lower part of the slide. And the lake continued up the Bitterroot Valley. So an immense lake, and you can really get an idea for just how big it was if you go to Missoula, and you can see these horizontal lines here on the hillside. These are strand lines from the lake, and they get up to be the highest ones are over 1,000 feet above the valley floor. So this was an immense lake that eventually broke through the ice dam and then flooded down through northeastern Washington state, creating the channeled scablands, getting into the Columbia River, and then in a few places and flowing out to the ocean. A few places it got backed up. Here at Wallula Gap, it backed up into a big lake all the way up to Yakima. And then at Kalama Gap, it backed up all the way to Eugene. And these floods took place repeatedly over a period of 2,500 years about. So as it would break through the ice dam, it would drain the lake, and then the ice dam, the ice would advance again and go across the river, dam the river again. It would back up, then eventually break through. And this happened repeatedly, maybe 40 or 50 times. There's some estimates that even more frequently, more often than that. But probably at least 40 events breaking through the ice dam and flooding down through the channeled scablands and out to the coast. You can see in the gorge a lot of scablands, especially if you get up towards the Dalles. And the scablands are just these. They're just remnants of bedrock. So you can imagine the flood coming through here, tearing up all the topsoil and tearing up a lot of the bedrock, and just leaving behind some remnants in places that are sticking up. And that's what we call scablands. If you drive up the gorge, you start really picking these things out. They kind of exist all over the place once you get a little ways up where it's a little drier. So for the Columbia Gorge, we see that the volcanic activity goes back to the early Cascades, and I didn't really talk about that, but we can see that in the older volcanic rocks, the Yohana-Pakash and the Eagle Creek Formation. But mostly the Columbia River basalt has a lot of interesting features, and like I said, we could go spend more time on that. But the age of the Columbia River, it dates back more than 12 million years. The bedrock structure, the southward tilt controls the shape of the gorge, making it very steep on the north side, pretty gentle on the, steep on the south side, and pretty gentle on the north side because of the landslides on the north side. And then it was the place where the Missoula floods or the Ice Age floods kind of all came back into the river channel and made their way out to the ocean. And if you compare this small place of what the Columbia Gorge is to the overall cross section of across Oregon, you can really get some perspective on the whole thing. You can see just how in this little area, or relatively small area, the gorge, there's so much to see. but it goes much, much beyond that. And you can see that there are all sorts of other features that one can explore in the state of Oregon and in Washington. And to really drive that home, let me just show this picture of Crater Lake, which, as most of you know, it formed from a giant volcanic eruption some 7,700 years ago. And Mount Mazama, which was a stratovolcano, kind of a typical size stratovolcano of the Cascade Range, erupted so catastrophically that it emptied its magma chamber and it collapsed downwards to make this big caldera. And you can see right here with Wizard Island that there was some volcanic activity after that eruption to make Wizard Island. And later filled with water. It's the 7th deepest lake that we know of on Earth. The water is incredibly clear because it doesn't have any streams flowing into it, and it's one of our first national parks. And it's Oregon's only national park. If you were to spend much time there, you would learn more about it. You'd start noticing these U-shaped notches, which were the old glacial valleys on Mount Mazama before it erupted. You could find places where there's bedrock that are Mount Mazama that dates back 400,000 years. You get to know all these interesting little things about it. And that's just one place. That's Crater Lake, which is one place, one volcano in the Cascade Range, which is represented by this triangle here on the cross section. And so I think that's something that I personally really love about being a geologist and working on these books, is always kind of exploring and finding new things, because those stories that we learn from looking at the rocks, they just go on, and you never stop learning. So thank you very much, and I'm happy to try to answer any questions you have.
Wow, what a tour, Marli. Thank you so much. And as a reminder to folks, you can use the little Q&A bubble at the bottom of your screen, and we will get to those questions in just a minute. That's a beautiful picture of the whole Crater Lake there. But if you could stop sharing, I'm going to share a couple more slides before we get to Q&A. Thank you. Okay. All right. I'll give you a break from all the talking for a second, Marli. So it's apt that that you're talking about things at the landscape scale tonight, because some of the challenges, threats, and opportunities that we're facing right now at Oregon Wild and across the country are also large in scale. So I want to just start by acknowledging that over the last few weeks, thousands of dedicated public lands employees have lost their jobs, from the U.S. Forest Service, the National Park Service, and many more agencies that do research, public education, community fire preparation, wildlife conservation monitoring, and so much more. And without enough staff, both public lands and visitor experiences will likely suffer. And not to mention what these mass firings are potentially doing to devastate small communities that depend on these jobs. So, and all of the funding that's been frozen that actually do some of the on the ground restoration work that I think we all value. So I just wanted to acknowledge that and then turn to what we can do about that and some of the other issues people are probably thinking about. So for one, while Congress may not be able to stop the disruption happening with federal employees, they might be, and they should hear from you that you stand with public employees. So Oregon Wild has a way that you can reach out to your Congress people with that message. And I will put these links in the chat in a moment. I can't multitask that well, but I've got links up here as well if you want to copy them down. and they'll come out in the blog posts and the recording that we send out tomorrow too, if anybody wants to actually click, because I know it's hard to do in a Zoom environment. So that's a message folks could send. And while public lands employees are under direct threat, public lands themselves are also under attack. It's pretty clear that the administration is intentionally creating dysfunction to justify gutting bedrock laws that ensure that agencies consider the best available science, meaningfully engage the public, and thoroughly analyze impacts of their proposals. As an example, Congress is considering the misleadingly named Fix Our Forest Act, which would roll back environmental protections and hand over control of more of our public lands to the timber industry. So we have an action to help you reach out to your legislators to voice opposition to that bill as well. And then if you've been on any of our recent webcasts or read any of our emails, you probably know about the proposed amendments to the Northwest Forest Plan, the iconic 30-year-old policy that helped transition national forests in Western Oregon away from destructive clear-cutting of our ancient forests to better conservation of streams, endangered and rare wildlife, and our older forests. So the draft amendment proposal is a mixed bag. We feel it has a lot of room for improvement on the conservation front. But on the plus side, the proposal includes more Indigenous perspectives and supports tribal sovereignty. So we have a lot of talking points and background information that folks can use to write your own comment. We have an easy way of taking action, which is to sign a petition, and we have a slightly more involved way, but really important, to submit a personalized comment on the Northwest Forest Plan before the comment period ends March 17th. So there is a link that's fairly easy to copy down that's on the screen right now. But also on Oregon Wild's main page, there's a pretty easy way to find Northwest Forest Plan stuff. And again, I'll put all these links in the chat for people to click on if they want to. So please do that. And then there's also plenty of action happening at the state level. So if you tuned into last week's webcast, you learned more about what we're tracking, and you can find that webcast recording on our website and our resource library. And one key piece of legislation that we're supporting is the 1% for Wildlife bill, which would increase the transient lodging tax to help fund desperately needed conservation programs within the state's wildlife agency. So there's a way to take action on that too. And then finally, if you want to learn more about what our staff are up to or any number of environmental issues, and you're in the Eugene area, consider joining us at the Public Interest Environmental Law Conference in Eugene this weekend. That's PIELC. We just call it PILC, pilc.org. And we have a blog post up on our website that has some of the panels that our staff are on and the website for finding out the schedule for that really wonderful conference. Now we will get to questions from Marli, or for Marli, sorry. And I'm going to stop sharing because that will help me see the questions better. Oh my gosh, they're stacking up.
Oh,
Well, I'm going to start with one of the first questions, and then I will gaze through them and see what I can pick out for our 10 minutes of Q&A. So somebody asked about, I think this was way back at the beginning, you mentioned the Alvord Desert and flooding there and wondering if that was a recurring event.
well, I would think so. I mean, it has some streams that flow into it that are probably typically pretty dry, but when at the end of the rainy season, I think you can expect it to at least be partially flooded. In the summer, if you go there in the summer, though, it's likely going to be dry. But so it fluctuates. It's like any ephemeral or lake or playa in Southern Oregon, I think.
Great, thank you.
And I don't think necessarily the whole playa takes a pretty big rainstorm to flood the entire playa, but it floods, I think, pretty regularly.
Yeah. Somebody noted that they have found pillow basalts on the top of Mary's Peak. And I know you couldn't get into all of the really interesting places. So the question is, did the rock erupt from the seafloor and eventually get accreted and uplifted, or was Mary's Peak an underwater volcano that then got accreted?
So great question. So Mary's Peak it's kind of got two main layers, if you will. The lower part of it, the lower 2/3, 3/4 are pillow basalts of Siletzia. The upper part, the very upper part, is gabbro, which is an intrusive igneous rock. It's kind of like granite, but it's much lower in silica. It's the same chemical composition as basalt, actually, but it's intrusive. And that's a younger intrusive body that makes the top of Mary's Peak. But the lower 2/3 is all, yeah, it's that Siletzia, and there's a lot of pillows in it. And if you've been to there's the picture I took was that I showed was on Mary's Peak in the quarry there. And I've only been there once because every time I go there and want to visit the quarry, there's people there shooting. And so I don't particularly want to go there when they're shooting.
Yeah, understandable. And could you remind us one more time what accreted means, just so we're
Thanks. Well, accreted just means added. So an accreted terrain is a basically a piece, a crustal fragment that has been added onto the continent.
Great, thank you. I know you kind of talked about it at the beginning, but okay. We had several questions about the Missoula floods, but the one that I think is maybe most interesting is about whether or how have the many Missoula floods changed the pattern or location of the Columbia River?
I don't think they've changed the location at all of the Columbia River. And they modified the channel some because they would have scoured it out some, but they certainly didn't create the topography of the gorge, which I think sometimes there might be some information plaques or something that say that the Missoula floods actually carved the gorge. The gorge was already there. They flowed down the gorge. But in so doing, they also scoured a lot of it. And some of the things like Beacon Rock is a volcanic neck, and it's really quite young, but it's older than the floods, and there should be more of the original cinder cone there, but most of the original volcano of the volcanic neck was taken away by the floods. So it's done things like that. And it transported a huge amount of gravel, which I was thinking of showing some pictures, but you can see big deposits of boulders. But in the Portland area, you have all these gravel deposits from the floods that are being mined for gravel, for aggregate. And up in Spokane, the Spokane aquifer is largely Missoula floods deposits, and it's a really great aquifer. The water is really high quality, and there's a lot of water in it, and it flows well and things like that.
Can you speak at all to an overlap between rocks and terrains and certain types of vegetation communities?
Oh.
Another lecture.
I know that there are some, like if you go down into the Klamath Mountains near Cave Junction, for example, there's what is it, the Rough and Ready pull out or something, or
Yeah, Rough and Ready Creek.
Is that what it's called? Okay, so those rocks there that make up the bedrock are high in magnesium and iron, and they have an unusual plant association there. I don't know what it is, but I know there's some endemic species that are just located there. There's also, I guess this is California, but if you get down towards the redwoods, the redwoods all grow on what's called the Franciscan assemblage, which is largely sandstone down there. And the moment you go across that terrain boundary and into some of these high magnesium and low silica and high iron rocks, they're called ultramafic rocks. The drainage is such that it's really crummy drainage, and the redwood trees stop growing like right there. They mark the boundary. But I can't really claim to know much about it. Those are a couple things that I think are pretty cool. But if anybody else wants to educate me on that, I would be delighted.
I'm sure there's botanists on here that
Yes.
can speak to that, but maybe for another time. Let's see. We have so many questions, so if you don't mind saying a few extra minutes to answer a few more, that'd be great. And if folks need to hop off, that's totally fine. So could you share just a few, actually, this is maybe a good final one. I'll save it for one more second. So someone asked about the Missoula floods, and then, you said the blockage in the Kalama area that then came down to Eugene. Was that part of the creation of the Willamette Valley, and did it contribute to it being such a rich agricultural area? Or that wasn't part of the question.
Probably contributed to the rich agricultural area because it brought in a lot of material that was deposited by the floods. So there was a lot of fine grained material in the old lakes and stuff that was deposited. I can't say for sure, again, because that's not something I've really focused on, but I'm sure that they did bring in the backwash. I mean, it all got backed up at Kalama Gap, and the backflow must have carried a lot of nutrients up into the Willamette Valley, and really didn't do, as far as I know, any scouring really. It mostly deposition. We know that it went as far as Eugene because you can find small, at least small. I've seen one pretty big boulder of granite that must have been an ice rafted rock that came from probably Idaho or Montana or something, because that granite, you don't see any granite like that here in the Cascades. So it must have been derived from somewhere else.
Got it. Yeah. Okay. I'm gonna scroll back up to one or two more questions. I had a couple of questions about the pillows. And were the eruptions that cause pillows like just a few catastrophic events, or were the volcanoes erupting continuously over a long time?
Well, my understanding is pretty continuously over a long period of time, about 6 million years. But one of the things I didn't talk about was just how huge an area or huge a volume Siletzia is. It's actually about 8 times the size of the Columbia River basalt group, about 8 times the volume. So it would have flooded North America to a depth of about 600 feet. So it's really an immense amount of volume, an immense amount of lava. And it's not all pillow basalt. There's a lot of sandstone in there. I mean, over a 6 million year period, there's going to be times of quiescence, and so things will erode and break down, and you get sand deposits and things like that. So there are some sedimentary rocks in there. There's even some marine sedimentary rocks. There's there's a lot of submarine lavas, the pillows, and there's even some lavas that probably flow down onto the land, like the plateau. This is probably a giant submarine plateau, and it was probably even emergent in some places. And you can see columns in parts of Siletzia. So I wouldn't view it as one big catastrophic eruption, but it was pretty active to create that much volume over about 6 million years.
That is pretty amazing to think that came up out of the ground. Yeah. All right. Well, I think I'm going to ask just one more question, and apologies to those who didn't get their question answered, but perhaps Marli would be willing to entertain an email. Or you can read her book, one of her books. But so this is a good one to wrap up on. Could you share just a few sites, and I know you've talked about some, in both Oregon and Washington that stand out as places to see geology? Like, point us to a couple of great places to go, you know, in our free time in the coming months.
Well, I often gravitate towards the coast because you good bedrock exposures there. And in the North Coast, I really like Humbug State Park. And kind of in the Central Coast, I really like Devil's Punch Bowl Beach. There's so much at Devil's Punch Bowl Beach. It's incredible. And then going to the South Coast, you know, the whole Brookings area is really cool. And I really liked Otter Point. I thought that's a pretty amazing. Well, Cape Blanco also. I mean, there's just amazing geology at both those places. I didn't write about Otter Point though in Oregon Rocks. That was one because I guess, well, it's really dramatic. I felt like there were places that had more complexity or things like that. So maybe Cape Blanco instead. If I were to go east, well, certainly the John Day area is pretty great. And of course, Smith Rock. The Oahe Reservoir is really awesome. And there's so many cool, and it's really colorful, lots of reds and all these different volcanic rocks. And then you can see dikes cutting through. The dikes are just amazing. You know, they're basically a dike is an intrusive body of, you know, liquid rock that is cut through an older rock, typically along a fracture. So it tends to be very tabular shaped. And they're just amazing dikes up around Lake Oahe. Yeah. Oh, and Joseph, town of Joseph. Oh my God, the Wallowa Mountains they just rise straight up out of the ground out along a fault zone. And there's a huge amount of geology in that area.
So basically what you're telling us is
Oh,
that there's a lot of really cool places in Oregon and Washington that we can see geology now that we have a little bit of better understanding. And we appreciate that. Every time I experience a geology talk, I learn something new and retain something new. So I hope that's the same for everyone else. This was fascinating and wonderful. And thank you so much for presenting to us tonight. Thanks everybody for being here. Again, we'll send out the links and recording tomorrow and pull a raffle winner. So again, thanks a lot and see you next week. Thanks, Marli.
oh, thanks. That was a lot of fun.
All right. Bye-bye.
Bye.